In the last topic, we have seen that the covariant derivative of a metric tensor is 0, right? So this helps us to define the Christoffel symbol in terms of the fundamental metric tensor. So in today's class, we will be seeing the definition of Christoffel symbol and its properties. Christoffel symbol. So we know that the covariant derivative of the fundamental metric tensor G mu nu is 0. This we have seen in the last class. By definition, I can write the covariant derivative of tensor as partial derivative with respect to x lambda G mu nu minus Christoffel symbol sigma mu lambda G sigma nu minus Christoffel symbol sigma nu lambda G mu sigma. Okay, but we know that the covariant derivative of the fundamental metric tensor is 0. Therefore, I substitute 0 is equal to partial derivative of G mu nu with respect to x lambda minus Christoffel symbol of sigma mu lambda G sigma nu minus Christoffel symbol of sigma nu lambda G mu sigma. Okay, now I can rearrange the terms. So I'll write partial derivative of G mu nu with respect to x lambda is equal to Christoffel symbol of sigma mu lambda G sigma nu plus Christoffel symbol sigma nu lambda G mu sigma. Okay, let this be equation number 1. Now I am going to define this quantity sigma, Christoffel symbol sigma mu lambda G sigma nu as Christoffel symbol of nu comma mu lambda. Okay, so when I write comma, you should not confuse with the derivative. So these are not the derivative, it's just a notation. Okay, so it's a Christoffel symbol nu mu lambda. Similarly, I can define G mu sigma Christoffel symbol sigma nu lambda as Christoffel symbol of mu comma nu lambda. So these are not derivative. You should not confuse with the derivatives. These are not derivatives. These are just a notation. Okay, so I can rewrite the equation number 1 because these two terms now I have defined in terms of the Christoffel symbol, another Christoffel symbol. Okay, so now I am going to substitute in equation number 1. So equation number 1 becomes partial derivative with respect to x lambda G mu nu is equal to Christoffel symbol nu mu lambda plus Christoffel symbol mu nu lambda. So let this be equation number 2. Now I am going to do cyclic permutation of the indices. That is, I have 3 indices mu, nu and lambda. So I can always do the cyclic permutation, which means mu will go to nu will go to lambda and lambda will go to mu. Okay, so this is known as the cyclic permutation of indices. So I am going to do cyclic permutation of indices. Okay, so in equation number 2, wherever there is mu, I will replace it with nu, and wherever there is nu, I will replace it with lambda. Wherever there is lambda, I will replace it with mu. So that is the cyclic permutation of indices. Mu will go to nu will go to lambda, and lambda will go to mu. So I am going to rewrite equation number 2. So here you can see partial derivative of g mu nu. So that will become partial derivative of g lambda mu with respect to x nu is equal to Christoffel symbol of lambda mu nu plus Christoffel symbol of mu lambda nu. Okay, so here you can see the Christoffel symbol in equation 2. Here instead of nu, I have written lambda. See, nu go to lambda, right? So this is the, likewise all the indices here I have done the cyclic permutation. Okay, so let this be equation 3. Now I am going to do one more cyclic permutation of indices. So now I am going to do one more cyclic permutation of indices. So again here this lambda will go to nu and mu will go to lambda, nu will go to mu. Similarly on the right hand side also. So I can write partial derivative of x mu with respect to g nu lambda, Christoffel symbol nu lambda mu plus Christoffel symbol lambda nu mu. Okay, so let this be equation number 4. So I have done 2 times cyclic permutation of indices. Okay, so equation 2 became 3, and one more cyclic permutation, 3 became 4. Now equation 2 plus 3 minus 4. So I am going to do this equation 2 plus equation 3 minus equation 4. Then I will get partial derivative of g mu nu with respect to x lambda plus partial derivative of g lambda mu with respect to x nu, then minus partial derivative of x mu, sorry, with respect to x mu of g nu lambda is equal to, on the right hand side, Christoffel symbol mu nu lambda plus Christoffel symbol nu mu lambda plus Christoffel symbol lambda mu nu plus Christoffel symbol mu lambda nu minus Christoffel symbol nu lambda mu minus Christoffel symbol lambda nu mu. So here I can cancel these two, then I can cancel these two terms. So the remaining terms will be 2 times this quantity, this plus this, so 2 times. Okay, now we have to, here I have done the assumption that the Christoffel symbol are symmetric with respect to the last two indices. So that's why here nu lambda and here lambda nu. So I assume that Christoffel symbol are symmetric with respect to the last two indices. So I can add these two terms. Okay, assume that Christoffel symbol are symmetric with respect to last two indices. Okay, then I'll get on the right hand side, this is equal to 2 times Christoffel symbol mu nu lambda. Okay, so for the time being we can assume that Christoffel symbol are symmetric with respect to last two indices. This is a property of Christoffel symbol, we'll come back to it later and we'll prove it. Okay, for the time being you can just assume that Christoffel symbol are symmetric with respect to last two indices. Okay, so now I can take this 2 to the other side, so it will become 1 by 2. Okay, so here I can divide this entire thing by 2. So I'll write Christoffel symbol mu nu lambda is equal to 1 by 2 partial derivative with respect to x lambda g mu nu plus partial derivative of g lambda mu with respect to x nu minus partial derivative of g nu lambda with respect to x mu. And this quantity, okay, which I am writing the Christoffel symbol mu comma nu lambda, so this notation we call that Christoffel symbol of first kind. So this is the Christoffel symbol of first kind. Christoffel symbol of first kind. So here we use the notation mu comma nu lambda, that is Christoffel symbol of first kind. So we have defined the Christoffel symbol of first kind here. See, so Christoffel symbol mu nu comma mu lambda is equal to Christoffel symbol of second kind. This is Christoffel symbol of second kind multiplied by g sigma nu. Okay, so Christoffel symbol of first kind is equal to, it is defined as Christoffel symbol of second kind, that is one contravariant index and two covariant index, that is Christoffel symbol of second kind. Okay, so this is the definition, and you can get the Christoffel symbol of first kind in terms of the fundamental metric tensor. Now let's do an operation with the fundamental contravariant metric tensor, okay, with the Christoffel symbol of first kind. So I am going to multiply g mu sigma. Okay, fundamental contravariant metric tensor I am going to multiply with Christoffel symbol of first kind. So right hand side also I have to multiply, right? So half as it is, now I have to multiply with g mu sigma, then this bracket quantities, right? Partial derivative of x lambda g mu nu plus partial derivative with respect to x nu g lambda mu minus minus partial derivative with respect to x mu g mu lambda. Now this quantity, the fundamental metric tensor multiplied by the Christoffel symbol of first kind, will give you the Christoffel symbol of second kind. So sigma nu lambda is equal to half g mu sigma partial derivative with respect to x lambda g mu nu plus partial derivative with respect to x nu g lambda mu minus partial derivative with respect to x mu g nu lambda. So this is called the Christoffel symbol of second kind, and this is the expression for the Christoffel symbol of second kind. So thus these equations give the connection between the fundamental metric tensor and the Christoffel symbol. So this is Christoffel symbol of second kind. Okay, so these equations give the connection between the fundamental metric tensor and the Christoffel symbol. Now in 4 dimension, if you are considering 4 dimension, then Christoffel symbol has how many indices? 3 indices, right? So 4 dimension and 3 indices. If you are considering 4 dimensions, then the number of components of the Christoffel symbol will be 4 raised to 3. That is number of dimension raised to indices. So there will be 64 components. The Christoffel symbol will have 64 components if you are considering 4 dimension. Okay. So first we started with the covariant derivative of fundamental metric tensor is 0, that we have already seen and proved in the last class. From there, from the definition of the covariant derivative, substituting 0, we get relation between Christoffel symbol and fundamental metric tensor. Then from there, doing cyclic permutation of indices, you will get 2 different equations. Then equation 2 plus equation 3 minus 4, rearranging, adding and subtracting, we will get relation between the Christoffel symbol of first kind and the fundamental metric tensor. Then multiplying the Christoffel symbol of first kind with the contravariant fundamental metric tensor, we get the Christoffel symbol of second kind, which can be written in terms of the fundamental metric tensor. In 4 dimension and 3 indices, the number of components will be 4 raised to 3, that is 64 components. Now we will see the properties of Christoffel symbol. Properties of Christoffel symbol. First one is the symmetry property. Symmetry property. Okay, so here we have assumed. So one here. So here we have assumed that Christoffel symbol are symmetric with respect to last 2 indices. Now we have to check whether the Christoffel symbol is symmetric or not. Okay, so let's check. So let a alpha be the gradient of a scalar function. That is, I can write a alpha is equal to gradient of a scalar function phi. Then the derivative of A alpha with respect to x beta. Now I am going to take the derivative of A alpha with respect to x beta. That will be, so right hand side also I have to take the derivative with respect to x beta. So already one derivative is there, therefore I'll write second derivative, right? So first I am taking a vector A alpha to be the gradient of a scalar function. Then I take the derivative of A alpha with respect to x beta. Similarly, consider another vector A beta, okay, which is the gradient of phi with respect to x beta. Now I am going to take the derivative of A beta with respect to x alpha, okay. Then right hand side also I have to take. So it will be with respect to x alpha and x beta. Now if you see these two equations, the right hand side of these two equations are the same, right? Then I can write that the left hand side should also be the same. Then I can write partial derivative of A alpha with respect to x beta is equal to partial derivative of A beta with respect to x alpha. Now consider the covariant derivative of A alpha with respect to B. So what here I have done is normal partial derivative. Now I am going to consider the covariant derivative of A alpha with respect to beta. So that I have to represent something like this. So with the covariant derivative with respect to beta of A alpha. So by definition it is partial derivative, right, with respect to A alpha minus Christoffel symbol sigma alpha beta A sigma. So let this be equation number 1. Now I am going to consider the covariant derivative of A beta with respect to alpha. It's given by partial derivative with respect to x alpha minus Christoffel symbol sigma beta alpha A sigma. Let this be equation number 2. Now I am going to subtract these two. Equation 1 minus equation 2. Then on the left hand side I will have covariant derivative of A alpha with respect to beta minus covariant derivative of A beta with respect to alpha is equal to, on the right hand side I will subtract these two, okay. Then partial derivative of A alpha with respect to x beta minus partial derivative of x alpha with respect to, partial derivative of A beta with respect to x alpha, then minus Christoffel symbol sigma alpha beta A sigma. Now minus of minus will be plus Christoffel symbol sigma beta alpha A sigma. Now here we have shown that this is equal to this. The partial derivative are equal, that we have already shown, which means that this will be 0, right? Because this term is equal to this term that we have already shown here. Therefore, the right hand side will be Christoffel symbol sigma beta alpha A sigma minus Christoffel symbol sigma alpha beta A sigma. Okay. Now here A sigma I can take common. So this will be sigma beta alpha minus sigma alpha beta A sigma. Now this term This term can be made to vanish by assuming that it is symmetric. But this happens only when we remove the gravity locally. Otherwise, in general, the Christoffel symbol is not symmetric. Okay, only when you remove the gravity locally, because the Christoffel symbol is actually dependent on the metric tensor. So, in order to make it symmetric, the only way is to remove gravity locally. So, the fundamental metric tensor is depending upon the geometry of space-time, which is in turn dependent on the gravity. Geometry and gravity are connected. Okay, so the Christoffel, this term can be made to vanish by assuming symmetry. So beta alpha is equal to alpha beta. That happens only when you remove gravity locally. Otherwise, it is not possible. So only in general theory of relativity we can assume that Christoffel symbol is symmetric. So in general, Christoffel symbol is not symmetric. Only in general theory of relativity, if you remove gravity locally, then the Christoffel symbol is symmetric and not in general. Therefore, the Christoffel symbol sigma nu lambda must be symmetric only in general theory of relativity, not otherwise. The Christoffel symbol of mu nu lambda. If it is symmetric, then I can write it as half of Christoffel symbol mu nu lambda plus Christoffel symbol mu lambda nu. So Christoffel symbol of second kind is symmetric in 4 dimension. If it is symmetric, then in 4 dimension it should have 64 components, but because of its symmetric properties, only 40 components are independent. Okay, in 4 dimension we have seen that it will have 64 components, but if it is symmetric with respect to two indices, then there will only be 40 independent components. Other will be same. If you know these 40, then others also you can find out. So if it is symmetric, then you have to find only 40 independent components. Now, if there is some torsion, then the Christoffel symbol is not symmetric. If there is torsion, then Christoffel symbol is not symmetric. In that case, it will be anti-symmetric. If it is anti-symmetric, then you can write Christoffel symbol mu nu lambda minus mu lambda nu. So in general theory of relativity, the Christoffel symbol must be symmetric and not otherwise. That is the important property of Christoffel symbol. Now we'll do a simple problem. Check whether Christoffel symbol of first kind is a tensor or not. Okay, that is problem number 1. Check whether Christoffel symbol of first kind is a tensor not. So we have to begin by transforming the Christoffel symbol of first kind. Whenever some quantity is given and you are asked to check whether it is a tensor or not, then you have to begin by writing the transformation law. Similarly, I write Christoffel symbol of first kind, mu, nu, lambda. This is the Christoffel symbol of first kind. I have to write the transformation. Okay. Then by definition, this is equal to half partial derivative of x prime lambda g prime mu nu plus partial derivative of x prime mu g prime lambda mu minus partial derivative of g nu lambda prime with respect to x prime mu. This is the definition. Now I have to write the transformation for each quantity, that is half partial derivative with respect to x prime lambda. Now g prime lambda mu, I have to write the transformation. So how do I write? Let g prime mu nu go to some g alpha beta. Then I can write partial derivative of x alpha with respect to x prime mu. Then x beta with respect to x prime nu. Okay, this is the transformation for g prime mu. Similarly, plus partial derivative with respect to x prime nu. Now I have to write for g prime lambda mu. So g prime lambda mu, so let it transform to g alpha beta. Okay, and then I have to write g alpha beta. Then partial derivative of x alpha with respect to x prime lambda, then x beta with respect to x prime mu minus, now the last term, partial derivative with respect to x prime mu. Then to again write the transformation for g alpha beta. That will be partial derivative of x alpha with respect to x prime nu, partial derivative of x beta with respect to x prime lambda. Okay, so I have written the transformation for these three quantities. Now I have to expand, I have to do the partial differentiation of all the three quantities here, then again here, right, and here. So it's a very long step. You should have some patience and you have to do. So this is equal to half, I'll write as it is, then partial derivative of x alpha with respect to x prime mu, x beta with respect to x prime nu, partial derivative of. So here what I am doing is, first I am taking the partial derivative of g alpha beta. So these two quantities will remain as it is. Okay, I'll take it later. Anyway, I have to take the derivative of all the three quantities. So first I focus on the fundamental metric tensor in all the three terms. Okay, first I'll focus on the derivative of g alpha beta. Then I will take the other two. So here these two terms as it is without any change. Now I am going to take the partial derivative of g alpha beta with respect to prime lambda. Similarly, in the other term also I'll write all the other quantities as it is, and I'll take the derivative of g alpha beta. Similarly, in the last term also I'll write all the other terms as it is and derivative of alpha beta. Okay, then again I have to take plus half. This half will repeat. Okay, now I'll keep g alpha beta as it is, and I'll take the partial derivative of the other quantities. Okay, I'll write in the next line plus half partial derivative of x prime lambda of this quantity. Similarly, in the second term, partial derivative of x prime nu of this quantity minus partial derivative with respect to x prime nu of this quantity. Okay, and g alpha beta as it is. Now in the first term it is done. Okay, here we don't have to do anything much, but here in the second term again I have to take the derivative. Okay, I have to open up all these brackets. So this is equal to half. The first bracket will be as it is, so I'm not repeating it. Okay, so this part is as it is. This is we have done. Then plus again half. Now I have to open up this part. That will be half second derivative of x alpha with respect to x prime lambda and x prime mu, then multiplied by x beta x prime mu plus now x alpha as it is. Now I'm not touching it. Now second derivative of x beta with respect to lambda and mu plus. Okay, so now we have done with the first term. This is done. Now we have to go to the second one, this one. Second derivative of x alpha with respect to x prime nu, x prime lambda, partial derivative of x beta with respect to x prime mu plus partial derivative of x prime lambda with respect to x alpha, second derivative of x beta. Now the last term, this term. So here there is a minus second derivative of x alpha with respect to x prime mu partial derivative of x beta with respect to x prime lambda minus partial derivative of x alpha with respect to x prime mu and second derivative of x beta with respect to x prime mu and x prime lambda multiplied by g alpha beta. Okay, so if you see here, this term and this term, okay, actually we can interchange alpha and beta, because the fundamental metric tensor G alpha beta is equal to G beta alpha, which means that we can interchange alpha and beta, and a few terms will get cancelled. For example, this term and this term will get cancelled. Similarly, this term and this term will get cancelled if I exchange alpha and beta. Now in the remaining term, I multiply and divide by partial derivative of x gamma, okay, and I have to take partial derivative of g alpha beta. This will be common term, so this common term I can take outside the bracket. So I am going to do two steps now: multiply and divide by this quantity and take this quantity common outside the brackets. So I can write, so I started with Christoffel symbol prime mu lambda is equal to half of, now I am going to do the first bracket, partial derivative x alpha with respect to x prime mu, partial derivative of x beta with respect to x prime mu, partial derivative of x gamma with respect to x prime lambda, sorry, here there's no bracket, plus partial derivative of x alpha with respect to x prime lambda, partial derivative of x beta with respect to x prime mu, then partial derivative of x gamma with respect to x prime mu, minus partial derivative of x alpha with respect to prime mu, x beta with respect to prime lambda, gamma with respect to prime mu. This is first bracket, multiplied by g alpha beta. So this I have taken common outside, plus, now the second bracket, there also I have to do the same step, x alpha, x prime mu, x beta, x prime lambda, plus x beta, x prime mu multiplied by g alpha beta. Now here I have to interchange alpha, beta, gamma. Okay, so this interchange has to be done in such a way that we can take this quantity common outside the bracket. So I'm just doing a manipulation of the given equation. So I'm interchanging alpha, beta, gamma so that I have to take this quantity common. Interchange alpha, beta, gamma such that this term will become common. So I can write mu lambda is equal to partial derivative of x alpha with respect to x prime mu. So this is common now, so I am taking it outside the bracket. Now inside the bracket I will have partial derivative of g alpha beta with respect to x gamma plus partial derivative of g gamma alpha with respect to x beta plus partial derivative of g beta gamma with respect to x alpha. Now second bracket I have x alpha x prime mu x beta x prime mu lambda plus x prime mu multiplied by g alpha beta. Okay, so here we can see that this term is Christoffel symbol of first kind. So I can write this is equal to half of this as it is. Okay, half of, so not half will also not come, because half will be with this bracket, then only it will become the Christoffel symbol of first kind. The definition of Christoffel symbol of first kind is half multiplied by the quantities in this bracket. Okay, so I can write x alpha x prime mu x beta x prime mu x gamma x prime lambda, Christoffel symbol of alpha beta gamma, plus now I have a second derivative here, right? So plus x alpha x prime mu second derivative of x beta with respect to x prime mu, then g alpha beta. So the first part will transform like a tensor, but the second derivative is actually making the Christoffel symbol of first kind as not a tensor, because the presence of the second derivative will not transform the Christoffel symbol as a tensor. So this term do not transform like a tensor. Therefore Christoffel symbol of first kind is not a tensor. So the problem was check whether the Christoffel symbol of first kind is a tensor or not. So we have started with the transformation of Christoffel symbol. First we have written the definition of Christoffel symbol. Then we have transformed it, or each and every quantity we have transformed to a new coordinate, right? Then we have to open up each bracket and then simplify. Once we have simplified, using multiplying and dividing by partial derivative of x gamma, and they have to take common outside this term. You have to take common outside, then it's a lengthier expression. So, and we interchange alpha, beta, gamma in such a way that we need this particular quantity common so that it will look like a tensor transformation. But unfortunately, in the second term, there is a second derivative appearing. Therefore, Christoffel symbol of first kind is not a tensor because it is not transforming like a tensor. Okay, so for today, we'll stop here.